Hello, I'm Kieran Sheila,
And I'm Tim Feldman.
and this is our project for Spring 2016 Microprocessors Lab. What we made was an arcade style controller using the
Embed USB HID library. So here we're going to start off with an overview of the hardware. There's a couple of things that we use in our circuit. You can note here that this is the Freescale board, of course, but it's connected to a custom connector board that I made. It's essentially an Arduino shield, but it suits our purpose perfectly. What we have here down is a junction board which connects to the buttons of our arcade controller and the lever. And in total, there's 22 different connections. There's 20 signals, one ground and one not connected. And over here you can see the USB header. This USB connects to the external of the controller and goes to the computer. But down here, tucked underneath, is a cable that goes directly to the board. On the top here, what we have is a board containing our LED drivers. And these drivers are necessary to drive LED RGB. So what we have here is the basic design of our USB packet. When we want to send data over USB, we need to have a standard format to do that in, and this is the basic definition of that. Because we're not using the thruster, the rudder, X and Y, we're basically just masking those. We're just filling them with ones. And what we're doing here, starting from bit 4, is where it really starts to get interesting. This is where our work comes in. So what we have here in this particular byte is kind of strange. You'll see here that we have a button with a mask of 4 ones, and then we're shifting it to the right or to the left. And the reason we're doing that is to make room for the hat input, because the way that we want this byte to be set up is hat first and then followed by buttons. And these buttons here will represent our first 4 buttons on our controller. It may seem like a lot, but our controller in total has about 20 different button inputs. And although only 4, or actually 6 of them are directly related to gameplay, the rest of them are contextual, and some of them are actually switches, not buttons, but they're very similar in operation. Our 5th byte here is simply just buttons. We have it masked such that the middle 8 of this byte is masked off, and then we're going to be shifting it to the right 4 bits to account for our 16-bit integer, which contains the value of all of our current button values. And finally, the 6th byte, which is our last in our packet, I guess it's the 7th if you start at 0, excuse me, will include a couple more buttons, 4 in total. So we have, I believe it's 16. That's right. That's the size of our integer here. But yeah, starting here, we have an interesting section which defines how our report is sent, or it's a descriptor of our report, which defines how the different inputs can affect the packet and how many buttons there can be, for instance. So we have a usage page which defines, a certain type of data that you might be sending, and then this particular value here lets the computer know that we're using a joystick as opposed to a mouse or another type of device. I just want to remind you that this is a generic USB device, so it's not like it has specific drivers that you need to have installed. Once you plug it in, it should work on any computer. That's the way it's designed, based on the USB standard. Of course, going on to the buttons, would be typo 9 on the usage page. And because we have 16 buttons, we have that defined here in hex. As I mentioned before, that our button integer is of length 16, so this is perfect for us. Our minimum and maximum give you the minimum and maximum values, of course, like I said before. And because they're digital, it's just 1 or 0. Pretty simple. The port is 1 bit per button. The port count, there's 16 of them to match the usage maximum, which are 16 buttons. And the rest is pretty self-explanatory.
So yeah, thanks, Tim. So yeah, just moving right along, we have this LED controller we made a little library for, where we're using it as SPI, but it's really just shift registers. So there's literally just a clock, a latch, clock, chip select, data, and output enable. And we're basically using the SPI library as a master out, slave in, except we're not using any input, just output data, 1 byte at a time, given a clock. That's the way our chips was designed, and it worked perfectly for application. So to simplify things, we made this little object with some methods to send bytes of data. Super simple. A little serial to debug, some arrays of stuff, which we'll talk about. Okay, so we're using a bus input to read all of our buttons, all 15 of them, plus a home button 16. That's special. We can talk about it later. And then the 4 hat positions. So we can read them as an integer and do bitwise operations on them. Super handy. So obviously they're pull-ups, they're common ground, that's the way we wired them, so we'll activate the internal pull-up resistors in the Freedom board. So to begin, we're basically sending 0 positions here by just that, making everything 0, everything's centered, throttle center, XY centered, button, nothing's being pressed, all that good stuff. For the LEDs, we need to write 3 zeros. We have 3 LED drivers, all feeding into each other, shifting into each other, red, green, and blue. So to make them all off, we have to shift in 3 zeros, bytes basically, just a whole byte of zeros, and then we'll enable the outputs. So, infinite loop. Obviously, run forever. Throttle is going to always revert to 0. Rudder is 0, X is 0, Y is 0. We're not using them in this design. If we want to, we can. They're right there. We can put stuff there if we want them to, but right now, we're not. So guess what? They're 0. Is up, is down, is left, is right is our diagonality check. That's also 0 because we're in the center. Okay, to give the button bus in information to the HID packet, we bitwise bitwise not it, sorry, because they're common ground. So when we press them, it's 0. We want that to be opposite, and then we mask it with 15 ones, 7 FFF, because there's 17 of them. So that gives us the correct size number. Unary operation, same deal. You know, this is just another fancy way to do a not. If it's 0, then give 1 to PS. Done. And then we're going to put that PlayStation home button into the 16th position in the button number by shifting it left 15. Reverse is just, the directionals also masked, put into, because it's also common ground. So we'll just breeze through this because this part's boring, but it's making sure there's no illegal directionals. Like you can't press up and down at the same time, or left and right at the same time. And that helps us get correct reports for the diagonal directions for the drivers. And I mean, that's pretty much it. And then we just shove that all into the HID driver, HID packet, and then it sends it. And then over here, when we check buttons, is when we activate all the RGB stuff.
Yeah, that's the fun part.
That's the fun part. It's kind of cool. Only 7 of them are backlit. So we have to iterate through 7 of them. And if we're taking the entire bitwise not of our input bus and we AND it with the power of 2 that is our current iteration, we'll get that 1 in the position of 1, 1, 1, 1, 1, 1, 1 for each button. So it's not accounting for multiple button presses, 1 button at a time. And we have this object, so if it's pressed, keeping track of basically if since the last iteration has been pressed, aka it's meaning it's being held down, we're not doing anything. So if that is the case, this isn't going to do it because it's not. So if it hasn't been pressed since the last iteration, aka you're not holding it down, that means this is the first time you're pressing the button. And we made it so it'll cycle through all the pretty colors that the RGB thing can allow us to use without PWMing, yes. Just a regular combination. So, else, button is not being pressed, obviously, we're turning them all off, but only for the current button which is not being pressed, the current button that you're checking. Last but not least, we need this delay. If we go too fast to this LED driver, then we're basically PWMing the output. We have to slow down this code so it doesn't turn on the LEDs we don't want it to when it's cycling through the drivers. And that's pretty much it for the code. Thanks.
Yeah, we'll run back and give you a practical demo.
So this is pretty easy setup. Literally, just run the USB cable into the computer, and then you do a little configuration to make sure all your buttons are mapped correctly in whatever program you're using. So, in all its glory, we're gonna watch Tim play some fighting games. Go ahead and do the hat toss. It's like